So now let's.
I have permission. It looks like it, yeah. Okay, so I should be recording now.
Dr. Luke, I can't really hear you.
See, let me close the windows real quick here. Is that any better, Lindsay?
Yeah, it is.
Okay, so a little bit less room noise. Okay, so I should be recording. Let me see if I can share my screen. All right, can everyone see my screen now?
Yep.
Awesome. Chat window, okay. Interesting, doesn't look like the chat gets segmented out by breakout rooms. That's kind of strange. Okay. Interesting. Okay, so before we start with what we're doing today, does anyone have any questions from what we talked about last time on Tuesday or Monday?
Hey, I have a question for Tuesday, Luke. Did you get a chance to look into the VR stuff?
You mean the robot simulator?
Yeah.
No, I have not had a chance to look at the robot simulator. Again, my thought process with that is I'd still rather try and get a robot at someone's place and do a remote thing there. Just because I don't know, I mean, I'll look at it, but I'm not sure how compatible the robot simulator will end up being with our code architecture and how we normally run things. Because it's not within the normal framework for the default framework. But I'll take a look and see what it looks like.
So this is Dr. B just checking in. Everything cool over here? You able to record? Everybody's doing fine?
Yeah, I think everything's working. The only kind of weird thing is I don't think that the group chat segments out by breakout room. So if we're posting stuff, I think we'll see each other. So I don't think it's a problem, just kind of a strange.
Yep.
That's
a Zoom thing. I don't think there's anything else we can do in that. We can explore other options, but right now I think you're right. So what I would do is you just add the comment, or you can send it to select people.
Yeah, that's true. Yeah, you can send it.
But it's only one person, so.
Yeah, I just tried holding like control down and it doesn't let me select multiple people.
No. Okay, cool. Just, you may preface it with LV or something if it needs to be just that. Otherwise, hopefully you can figure out the chat as you're doing it. You'll figure it out. All right. You guys have fun.
Okay, we will.
We're not having fun.
Not having fun? Okay, well, let's see if we can do some math, and then we'll have fun with the math. How does that sound?
Already did math today.
Well, you can always do more math, Alex. There's no such thing as too much math.
Bad math.
Okay, so well, let me just start with a little bit of a review of what we already covered with the PID before we jump into the next set of things. So let's see here. Let me get my drawing tools up. Let's see. All right. So last time we had two plots, and one of them was the thingy that moves as a function of time. And then we always had some goal that we were trying to get to, a set point. And we also had a starting point too. And okay, so sorry, that's the neighbor's dog there. Okay, so okay, so let's start with this then. Can someone remind us what the P stands for in PID?
Proportional?
And what does that physically do to get us closer to, get us from our starting point to where our goal that we're trying to get to?
It's proportional to the amount of error between where we're at and our set point.
Okay, exactly. And so since it's kind of hard for you guys to describe how to draw something, actually, no, you can draw on your side. Can someone draw what the curve might look like in orange if we just had the proportional control? I think you guys should be able to draw on this.
Wait, how do we draw?
If you go up to the very top, you should have an annotate button, I think.
Oh, wait, is it capital I? No, oh.
Sorry, that was very, very, very bad. Did you see it?
I can see it. You want to try it again?
Yeah. One more try, I can do.
Okay, I believe in you.
Go, Alex.
Okay, so looks good. Sometimes, so that's what the curve would certainly look like if we had a pretty low proportional coefficient. So we just took our time and went very slowly to our set point. If we went a little bit faster, we do tend to get these kinds of oscillations, right? Remember those? So what term would we tweak in order to get rid of any oscillations that we would get?
The derivative.
Okay, that's our D term. Okay. And then can someone draw with the curve? I'll erase this. What the curve might look like if we've got that just a P and a D term. Okay, awesome, perfect. So we start out getting closer to our goal, and we've got a little bit of oscillation, then we dampen that oscillation out. Awesome. So so can someone remind us what the I term stands for in PID? Interval. And what does that fix for us?
It fixes the steady state error, which is the margin of error that we have constantly, sometimes between our set point.
Okay, awesome, perfect. And then can someone talk about the feed forward controller?
That's what applies constant power so that the thingy stays steady, like in the same position, maybe fighting against gravity or some sort of friction or something.
Okay, yeah, so it is some amount of power that's being applied to the system in order to maintain its state, usually to fight against gravity or friction in, say, the shooter. Only thing I change with your definition is that typically we do use a constant power, but it doesn't have to be a constant power. So for example, if you think about Cheesy Proof's arm last year, when the arm is, like when the elbow joint is fully retracted, it takes a different amount of force to move the elbow joint than when the elbow joint is fully extended, right? So when it's completely vertical, it's pretty easy to move the elbow right around vertical. When you extend it out and it's sort of being held horizontally, the lever arm that you have is substantially longer, and so it takes more force or more torque on the motor in order to move it about the horizontal position. And so they almost certainly used a feed-forward controller that applied a different amount of power based on the current position of the arm. So you can model your system in different ways to have a non-constant amount of feed-forward power. Does that make sense?
Yep.
All right. Any other questions on what we've already covered with PID before we dive into what we're talking about today? Okay. So last time we had the two plots. One of them was the thingy that moves plot, and the other one was the power plot. The plot that I didn't show, because it's sort of hard to fit 3 plots on here at the same time, is the error plot. And so instead of having the power plot today, know that it's happening, but we're just going to have the thingy that moves plot and the error plot. And so I'm going to go ahead and make that. Actually, I wonder if I can copy this. Copy. I got excited, but I don't think I can copy this. No, okay. This is here. So, let's see, oops. All right. Okay. So when I talk about the error, we are defining the error as follows. So we're defining the error as this distance between the current value at a given time of the current value of the thing that moves at a given time compared to the goal that we have. And specifically, we define it as error, which I'm going to call E, equals the we'll call it the goal minus the current value, which I'll call C. Let's see. Okay. And so if we're below this goal, our error is positive. So right here, the error is positive, whereas up here, the error would be negative. Does everyone see that? Okay. So if we were to draw the error plot, you would end up with something like this. So we would start out with a fairly large positive error, and then let's see, thinking here. You know, we'd have something. I'm just going to do kind of a simple curve here. We'd get to this point, all of a sudden our error would start going negative. And I'm not saying that it has to be sort of these sharp angles. It's just a little bit easier for me to draw it here. It is actually, sorry. Let me just do it correctly. One second. Okay, so here, let me just draw the error curve properly. So because of the way we sort of set up the graphs, it's going to look kind of like a flipped version of a flipped and shifted version of the thingy that moves plot. Does the error plot make sense to everyone? Okay. The other thing I want to say is that the error is a function of time. Is there anyone on the chat in this breakout room right now that hasn't worked with functions yet? Okay, awesome. That way I just sort of know what terminology to use and what terminology to explain. Okay. So does anyone remember why we care so much about what the error value is when we're doing the PID algorithm? So we've got the total power that we're going to be applying to our system, okay? And it is a combination of the power from the proportional controller plus the power from the integral controller plus the power from the derivative controller plus the power from the feed-forward controller. Does anyone remember that? Anyone have any questions about how we get the total power as a summation of the powers that we would get from each of these 4 different components of the controller? Okay. So when we look at this, the proportional power is a function of the error. The integral controller is a function of the error. The derivative controller is also a function of the error. And then the feed-forward controller could be a function of a variety of things. Sometimes it's a function of nothing because it's a constant value. Sometimes it could be a function of the position, so it could be a function of thingy that moves. Sometimes it could be a function of the velocity of the thing that moves. So the feed-forward controller, which we won't spend too much more time on today, could be a function of any number of things. And so the overall, in order to calculate the overall power, you are a function of the error and then whatever the feed-forward controller is. So if the feed-forward controller is just a constant number, then all you need to calculate the total power that you're applying is just the current error, is just the error values. Does anyone have any questions about what I mean when I say these are a function of the error? Okay. So in words, can someone tell me, let me see if I can just hit this. So, function of the error. Does anyone remember in words, what the equation is for the proportional portion of this?
It's the proportional constant times the error.
Okay, exactly. Okay, so, and this is the error at a specific time, right? This is the power that we're applying here is at this specific time is calculated with this specific error. And all we have to do to get this to work as an algorithm is to plug in our equation, this error equation here, right? So this is equal to just Kp times G minus C. And we can calculate that pretty easily, right? Does anyone have any questions on how we get the equation for the proportional portion of the total power that we're applying. Okay. In words, can someone talk about how we calculate what the function is for the derivative portion of the total power? You don't need the equation. Does anyone sort of remember, just in words, what that equation is?
It's the derivative constant times the change in our error.
Okay, I like that. Change in the error. And to be more mathematically precise, that would be the derivative constant times the derivative of the error. And there are a million ways to write in math notation the derivative of something. And unfortunately, I'm trying to see if there's any options on here that would let me do any good ones. So what I will do, I will just draw it out. I don't think it's going to let me see something real quick. We're going to try and experiment. I do. See that one insert. Apparently not. Okay. So that doesn't quite work. Okay. Wait, but it might be mine. No, okay. That's not work. Okay. So that doesn't quite work. So I will just draw it out and apologize for my messy handwriting here. So one of the most common ways to do this would be to write this as K sub D times D E dt. So here we have the derivative coefficient that we've been working with. That's that one there. And then this right here is the derivative of the error with respect to time. So t being time. So let me just make that clear as well. Okay. So whenever you calculate the derivative of something, you have to calculate the derivative with respect to some other variable. And everything that we're going to do today, we're going to be calculating the derivative with respect to time. Does anyone have any questions about the notation here? Okay. In sort of simple words, does someone want to talk about what the derivative is, what the derivative of a function is? Gianna, have you started with derivatives yet?
I don't remember it if I have.
Okay,
That's a
that's fine.
calculus thing.
Changing the slope.
Say it again, Alex.
It's the, what was it, change in the slope of the line? It's like smooths it out, right? So it's like a square root sort of thing. Like small.
I don't know if I'd call it a square root. So physically what the derivative is I'm going to use blue as the derivative. The derivative is the slope of the function. So right here, where I'm calculating the error here, I can approximate the slope by this thin blue line right here. at each point, anywhere in the curve, I can draw a line that is basically tangent to that curve. And I'm just calculating all the slopes, right? And if I were to then plot the value of the slope here, and 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 the value of the slope here, I would have another function. And that would be the derivative of that other function, the blue function, would be the derivative of the orange function. And I could then look at the values of the derivative function and know the slope, or in our particular case, the change in the error at any given time. So let's see, does that conceptually make sense that the derivative describes the slope at every single point in time along this curve?
Yeah.
Okay, so let's start with a simple one here. So let me make another plot. So we've just got, here, I'll be consistent. I will call this axis the time axis, and this axis the error axis. Okay. And if I draw, let's see, do this. So if I have an error that is constant over all time, what would the derivative look like of that function?
Would it be 1?
So what is the slope of, let me ask it this way. What is the slope of the error function, right?
It's 0.
Yeah. And actually, let me just fix this, fix the color here real quick, just so we don't get lost. So I'm going to use red for error. But yes, Alex, you're correct. So the derivative of a horizontal line is always equal to 0. And so the function dE dt is this blue line that hugs 0. Does that conceptually make sense?
Yep.
Okay. So if error equals some constant, I'm going to use, let's see, I'm going to use A as a constant just because we're already using K's and C's for things. So A is just some generic constant. So the derivative of E then, now I should be careful here. Another way to describe, so let's see, this is error as a function of time. Another way to say dE dt is E prime with the little tick mark. So that is this, let me see if I can, so people don't forget. So that would equal K D E. So it's just a different way to notate the derivative with respect to time as E prime. So the derivative of that equals 0. Does anyone have any questions with either that conceptual part of it being 0 or what it looks like when it's written down mathematically? Okay. So let's go to a more complicated curve slightly. So if we've instead got an error that looks like, that, so it's a straight line that's starting out negative and going positive, what do you think the derivative of this curve would look like?
Almost one, maybe like, not one, but like 1/2 or something.
Okay, but it'd be some constant number that would equal its slope, right, Alex?
Yeah.
Yeah. And so if we'd done instead a line this way, what would its derivative look like?
Negative.
Negative, exactly right. So
Plus E.
say it again.
My dad wants me to say plus E, but I don't understand. You're asking me what the slope is, and the slope is
Where it crosses where it crosses the y-axis.
no. That's the
No.
y-intercept.
Alex is correct. We don't need a plus E anywhere in here for calculating the slope.
Not for
So,
calculating.
yeah, so here, so if we go and write that mathematically, so the second thing we had was E as a function of T is equal to, I'm going to use, I know M is usually used as slope. You'll see why in a second, but I'm going to use B as the value of the slope times time plus some constant A. So that was the equation for one of these red lines. And then the derivative of that is equal to just B, just the slope of that line. Does anyone have any questions with the conceptual part of that or with writing it out mathematically? Okay. I will now go to one more harder curve. And then I'll talk about why we're going through this trouble. Okay. So the next curve option is what if our error looked like that? What do you think the what do you think that the derivative of that function might look like?
It's a change. It changes.
Okay. So how about let's walk through it one step at a time, and we'll just plot it manually. So Lindsay asks, always positive. Not going to be completely always positive. Let's walk through it. We'll just go step by step. So what is the slope here at that point where I just drew that line?
Negative.
Negative, okay. Is it very negative or kind of negative?
Kind of.
Very.
Very? I'm going to say, it's all relative terms. I was going to say that it's going to be very negative. And maybe you guys can see why in a second. So I'm just going to put it there. So the, oh, that's be blue. Apparently hearts can't be blue. Apparently hearts can't be blue. Let me see if I can do it. That doesn't make any sense. Do a star. Stars can only be gold and hearts can only be red. And check marks can only be green, but arrows can be any color you want. Let's see. Let me see, draw. Okay, so Lindsay asks, how can that be very negative? It's only a few degrees east of south. Okay, good question. So if we define a slope of 0 as being horizontal, then the steepest slope you could possibly have is if you were completely vertical. And this slope right here is a little bit, reasonable amount closer to being completely vertical than it is to being horizontal. So just for the sake of how we're going to describe things, I would call that pretty negative. Does that answer your question, Lindsay?
Yeah, I was going in reference to the y-axis, not the x-axis.
Not a problem. Awesome. Okay. So let me put that right back there. Okay. So how about the slope right there? What does that one look like?
It would be less negative, correct?
It would be. So is Michael.
I have
Okay.
a question. So would the shape be going up and then eventually going up from Earth connecting and then eventually stopping at 0, and then repeating the same pattern except going in the except going up positive, creating a bit of an, I'm not sure how to describe this shape, but
Okay. Well, how about we'll just continue plotting it, and then we can see if that shape is what you were thinking of. I think you're going in the right direction. Okay. How about the slope right here at the bottom of the parabola?
it
No,
would be 0.
very
So
It'd be what?
0.
zero.
Awesome. I'm just going to say this parabola is a little bit off to the side here, so I'm intentionally not putting it right in the center there. Let me just fix that a little bit. Okay. How about draw? Okay. How about the slope right there?
it'd be slightly positive.
Slightly positive. Okay. And then last but not least, how about the slope up here?
Very
Very positive.
Very positive. Actually, line up there. Okay. And so what we find is that the derivative of a parabola is a straight line.
Luke, I would just like to let you know that I said that. My dad's like, no, no.
Well, sometimes you need to bring data to your dad in order to prove him wrong.
View it, Dad.
So, does this satisfy you, Mr. Shanfield?
There's a very perplexed look on his face, staring at the screen.
Okay. Well, maybe he'll look a little less perplexed here in a little bit. Does this conceptually make sense, how we figured out the derivative of the parabola?
Now it does.
Okay, awesome. So if we were to look at that mathematically, our parabola equation, and again, I think I'm using the letters backwards from how they probably teach it normally, so I do apologize for that, because I'm going to call this C as a constant times t squared plus b times t plus a. And the derivative of that parabola equals, this is the fun thing, 2 times c times t plus b. And what I'm going to do is I'm going to go back and fill in something. Well, so before I fill in something, does anyone see a pattern with how we're calculating the derivatives here?
You're adding a new letter in front times everything that's behind it.
You're adding
Okay.
another, it's like making it to the power that it's actually at. Like when it was a constant, it was only had one input. And then when it had one value changing, it only had one input, like the change. And now it has 2.
Yep. Okay, so so everyone else gets on the same page here. Let's set this up very consistently. So this constant a was actually a times t to the 0 power. Okay, and so that was then 0 times a times, it's not really defined. I don't want to put t to the -1 because that's really not true, but you end up with a 0 times in the front and you end up with a 0, right? And if we looked at this one, that was b times t to the 1 power plus a times t to the 0. And so what we really had was 1 times b times t to the 0 plus 0. And what we really have here is b times t to the 1 plus a times t to the 0. And our answer was really 1 times b times t to the 0 plus 0. And so our pattern is we take the exponent from the original function, we bring it down from the exponent and make it a multiply, and then subtract 1. So we bring the 2 down, and then 2 minus 1 is 1, so I should have put that there. And then we come over to here and we say 1 times b, and 1 minus 1 is 0. So now we get a 0, and then for the constant, we're already at 0. So when we take the derivative of the constant, we just get a 0. Does that pattern make sense? Does anyone have any questions about that pattern? Okay, so this will be the last one that we do here. If I have e of t, e is a function of t. Okay. So Lindsay asks, can we go over how to get the exponent? So, and maybe this example will help make that a little bit more clear. To get the new exponent, it's the old exponent minus 1. And let's do this example and see if it makes any more sense. So we're going to start with e equals d times t to the 3rd power plus c times t to the 2nd power plus b times t to the 1st power plus a. Can someone walk the group through what the derivative of that function would look like?
We would have 3 times d times t squared.
Okay. Plus?
2 times c times t to the 1st power plus
Yep.
1 times b
1 times
t to the 7th power plus 0.
1 times b times t to the 0. Yep. And
That's
then plus 0, right? Yeah. Okay. Does getting the exponents make sense, Lindsay? After seeing that one?
Yeah, I just kind of forgot what you said it was.
Okay. That's okay. Does anyone else have any other questions about this pattern now? So this pattern only works for polynomials. Fortunately, and so like if we have a more complicated function like sine, like if we wanted to do the derivative of sine, we need a different method of mathematically doing the derivative. But for polynomials and things like that, this pattern works great. Did anyone have any questions about what we've covered so far before I go on and talk about how we actually calculate the derivative in code? Okay. So let me I'll just put that off to the side for right now. I'll be able to grab it later if I want. And I'm going to erase this. Okay, so I showed you all how you might get a derivative from a polynomial, whether that's a line or a quadratic function or any of those. Now, our error plot, this one right here, is not a polynomial, right? It's some complicated function. And in reality, because you know, this error is based off of a sensor reading and it's based off how the motor moves and everything, it's not going to be a function. There is going to be no way to directly say that, you know, there's not going to be a way to write E as a function of T for this, because it's experimental data. It's data you're collecting in real time. It's not a nice clean function. And so if I just draw just sort of a random curve here, okay, does anyone have any thoughts on how we might calculate the derivative at a, not for the whole thing, but for just a specific point? And I want to do that point right there, and just so we're all kind of see it. And what I would think back to is what our definition of the error was. Does anyone have any thoughts on how we might estimate, calculate or estimate what the derivative is at that particular point in time? Alex, do you have any thoughts?
Which derivative are we calculating? Is it the drawing thing?
Yeah, so right over here, I don't know if you guys can see my mouse or not. The bottom right-hand plot, I've drawn sort of a random, and I'm sorry, this should have been red. Keep with the pattern here. So this is the, let me see if I can start with a line that matches what I drew before. So we've got our error function here, and it's not a nice clean function like a parabola. So how might we go about calculating or estimating the derivative at that specific point?
Do we need to gather a few of the points near it and then find the slope?
Yeah, we can do that. That was actually going to be what the next solution I was going to propose. So let's hold on to that. That is the plan that we're going to implement. Is there a simpler one that we could try? So what if, or maybe I misunderstood, maybe you are describing the simpler one. So can you say what you said again, Alex?
Oh, we take a few of the points like near it, and then we calculate the slope.
Okay, so like if I took this point here and this point here, it's like a point on either side of it. How would I calculate this? How would I calculate the slope? Okay, I think we're on the same page now. How would I calculate that slope?
With the slope formula, like how you normally calculate the slope.
Okay, so we'll call this one 0.2 and that one 0.1. And we need to calculate, and we're going to call this we're going to call this E of time now. So this center one right here is now this center dot. Okay, so why don't you walk me through what the normal slope formula is, Alex?
y2 minus y1 over x2 minus x1.
Okay, and in these units, or in these nomenclature, right, that'd be E2, sorry, E2 minus E1 over T2 minus T1. Does that make sense to everyone out there? Say it again.
I said yes.
Okay. Does that make sense to everyone? Has everyone seen the slope formula before? Okay, so we can do that, and that is sort of the easiest way that we could calculate or estimate the derivative right at that point in time. When we're looking at this thing in real life, the curve that we have is actually made up of a series of points, right? Because they're discrete sensor readings that we get from our sensors, and we're measuring them once every loop cycle. And so, oh, I'm sorry, these should all be red. See if I can, oops, redo. Let's see if I can. Imagine that these ones over here are red too. They're consistent and failing here. So we've got all these points, and so it's actually kind of easy for us to calculate the derivative. I'm sorry, that should also be, oops. Come on. Let's see if I can grab that. Okay. That is apparently now stuck there and cannot move. One thing that I just noticed is there should be a prime mark here, right? So that was the derivative that we were calculating, not the error. So it's actually kind of easy to do this, right? We've got all of it. We've already got everything in a set of a series of points. So we could take our point that we care about and then look on either side of it for 2 points and calculate those. Can you think of any potential problems that we could have with this method in the real life scenario?
It doesn't get it, like it's not a big enough slope.
Can you talk about that a little bit more?
Like you don't have a big enough data gathering, like a big enough like thing to check from.
Okay, yep. So that's exactly right, because in real life, our nice sensor curve is never going to be this smooth. Our sensor curve probably looks something like this, right? You've got some noise on top of, it's still got the same general shape, but you've got some noise on top of it. And so depending on exactly where you take these 2 points, oops, right, wherever you take these 2 points, it could dramatically change the slope value that you're calculating, right? Does that make sense to everyone? Okay. So what would be a solution to calculating the derivative robustly, even in scenarios where the curve that you're trying to calculate the derivative of is bouncing all around and is not particularly smooth? And I don't know that anyone in this chat has gotten to this part of math yet, but that's okay.
Could we try to like fit a function that approximates the general shape of the curve?
Exactly.
Line?
Say it again, Alex.
Do we need like a best fit line? Like, where in stats, like a correlation thing?
Yep. You guys, both you and Juliana and Lindsay has posted in the chat. Linear regression, best fit line, fitting a function, all of those things are exactly correct. So we would take some subset of points. Maybe, we would decide how many we wanted. Right, we've got maybe that one, that one, that one, that one, and that one that surround the point that we care about, and we would fit some function to it. And we could start out with just fitting a straight line to it, and it's really easy to calculate the slope because like the equation of the line, like the derivative, because the derivative is just the slope of that line. Or we could calculate or we could fit a more complicated function, like a polynomial. And in the case of the PID algorithm that we use, we fit a third-degree polynomial function. So we fit one of these functions to a subset of points that surround this point. And once we fit the function, and LabVIEW just has a block that will do that for you, you can then very easily calculate the derivative of that function at that particular time. Sorry, that should be a t. Sorry, d times t. And so we can get that derivative, right? And then what we would do, so if we had, let me see what I can do here. So I don't know if I can copy and paste. I cannot. Okay, thanks. Okay. So we would fit this curve to a subset of our points. We would take the derivative of it, okay, and then we would calculate that derivative at a specific time, at t equals now. Right, so we would have 3 times d times now to the second power plus 2 times c times now plus b. And this value here, let's see if I can, this value here would be this slope, an estimate of this slope at that time now. Does anyone have questions about the idea of fitting a polynomial curve instead of just a line to a set of points, and then taking the derivative of that fitted curve, and then what we say is evaluating that derivative at a specific time in order to get the slope or the derivative of the original function at that time? Any questions or concerns? Okay, so that is how we calculate this term right here in the code as it stands right now, is we fit a third order polynomial and take the derivative and evaluate it. Before we move on to the integral term, I'm going to have a question for you guys. How many points should we fit? How many points do we use in order to fit the polynomial to it?
Over 5.
Okay. Why over 5?
Because a third-degree polynomial has 2 curves, so you would need 5 points, like, to have all of the curves, or like the maximums.
Okay. I think you can get away with 4 points. So if you need 2 points for a straight line, 3 points for a quadratic, and then it should be 4 points, I think, if I remember correctly.
Oh, yeah,
for a polynomial. Yeah, okay. For a third-degree polynomial. Is there any advantage to using more than 4 points?
more reliability.
Okay, more reliability for sure. Lindsay says you get a smoother curve. Absolutely right. What if we used 100 points? What are some of the would there be any problem?
Yes, because then our rapid changes wouldn't be detected as quickly.
Exactly. So imagine trying to fit, if we had a very complicated curve, we had a very complicated error curve. I was doing all sorts of weird things. If we use points that were all over this curve, like all along the length of the curve, when we try to fit the polynomial to it, the polynomial is not going to be able to approximate this shape very well. And so when you calculate the derivative is going to be more incorrect than it could be. And so you really have to balance this decision between having more points so that you have a smoother approximation that's more stable, and then only looking at points within a local region, you know, to a region of the error curve that is small enough that the function that you're fitting to it can reasonably be expected to describe or approximate that curve. If you try to fit it to too large of a section of the curve, it's going to have trouble describing that curve. Is there any other, I mean, those I think are the two, that's the primary trade-off. Does anyone have any other thoughts on what a problem might be, thinking about maybe what the moving average filter that we used? So one of the other things that can happen is if you have a very large number of points that you're trying to fit the curve to, it'll be just like if we had a very wide window on the moving average filter, and we'll have some latency. So again, quick changes or a change in the curve, even if it's not that quick, won't show up until later on. So there'll be a lag. And then also, if you have, the more points you have, the more computationally expensive it is in order to do the curve fitting. So it'll actually take longer for the RoboRio to calculate it. So you get some additional delay there. Does anyone have any questions about anything we talked about regarding the derivative? Okay, awesome. So let's move on to this, the integral. Let's clear some space here. Okay, that is a race. Okay. So the power portion that's coming from the integral term, also a function of the error, and it's going to equal, so this one we want to talk about in words, what the integral, with this integral portion equals functionally. So we've got the k sub I term, right? The integral coefficient, and it's going to multiply by something. Does anyone remember physically what the integral is?
It's that's the error over it's multiplied by the error over the time window.
Okay, yep. So this is the error over the time window. More strictly, that is ki times the area under the error curve, and I'll draw that in a second. And then even more strictly, that would be ki times integral of the error. And I will do is make that larger, give us some space there. Okay. Ooh, that's interesting. I'm unsure as to why that moved down there, but that is where that is, and I can't move it. So, So what I mean by the area under the curve is the following. So let's see what my options are here. We're going to use pink for, or this lavender maybe for the integral. So if my time window that I'm calculating the integral over is inside of the lavender box here, let me see if I can get rid of some of these slope markers, then the integral, little brush, oh, perfect, is this area here plus this area here. So do you guys think that this area is positive or negative? This one up in the first portion of the area.
Positive.
Positive, yep. And then the area that is in this direction is negative, and then we've got another little piece of positive area here. And so the integral of this curve will be the summation of all of the areas underneath that curve. And so your integral is going to be big if either the value of the error is, oh, I'm sorry, I kind of screwed up. We are calculating the integral of the error, not the integral of the thingy that moves curve. I apologize. And these slope markers that I had the slope markers should also have been on the error curve and not on the thing that moves curve. So I apologize for that. Does everyone see where that mistake was? Any questions about what I mean when I say I should have put the slope markers on the error curve instead of the thing that moves curve? Okay, so let me draw the integral here again. So we've got that area, we've got that area, and we've got that area. Okay. Now, so the integral is going to be large if either the error is large and or if the amount of time that the error is medium for is large, right? So you could have a function where, let me do this, red, oops, red, red, okay. You could have, two error functions, one that, looks like that and goes on for a very long time. And it's got, let me do this a little better. Right, so you could have, I'm just going to use the two halves of the axes just so there's two functions. So you could have one error function that kind of looks like that, and it's got all sorts of area underneath the curve here, right? Then you have another error function. Let me do that one more time. I apologize. I want to show something specific here. You could have an error function where it starts off pretty large and it gets pretty small pretty fast. And it's got some error underneath the area underneath the curve. Okay. And then you could have another error function that stays kind of medium sized but lasts for longer. And both of these different error functions might have similar amounts of area underneath the curve. Do these two plots make sense to everyone? Or is there any questions?
How do we find the integral of the curve?
Awesome question. So let me talk about it in two ways. So number one, if you have the function for the curve, there are ways to calculate the integral mathematically. And I'm not going to go into them in great detail today because we don't end up doing that for our math. But essentially, you run the derivative backwards. So the integral of this function here is this one. And the integral of this derivative is this original function. There are nuances to how you handle constants and some shifts and stuff, but mathematically, the integral is the opposite of the derivative. Now, because we don't have functions to begin with, and because calculating the integral based off of a fitted curve is probably not what we want to do, and we can talk about that more in depth later if you guys want. There are going to be some noise problems associated with that. We're going to take a different approach to calculating the integral. And I think you guys can probably figure that out pretty quickly by yourselves what that approach is going to be. So if we're looking at this curve right here on the left-hand side, and it's just a perfectly straight line, since you asked the question, Juliana, how would you calculate the area underneath this curve?
It would just be a rectangle, right? So like, or close to that. I'm not entirely sure.
Okay, absolutely right. It's a rectangle. So, you know, the area of that one would be, so I'll use capital A for area. That area would just be, let me see if I can name some other things. We'll call this, we'll call how wide it is W. Well, for reasons that will be clear in a second, so it matches formulas you've seen before. The width of this, I'm going to call H. So that is the measurement from, let's see. Let me see if I can find a tool. Oh, perfect. Okay, so H is that dimension, and then we'll call this other one A. Again, for reasons that will be consistent with formulas you've seen before in a second. So the area would just be for this rectangle, A times H. Are there any questions with calculating the area under the curve for just this piece using a rectangle? Okay. So, follow-up question. How might you calculate the area under this more complicated curve? And it's okay to approximate. It doesn't have to be exactly the area. It just has to be an approximation of the area.
Could it be? Never mind.
So Lindsay asked, could we break it out into other shapes? So what if we broke it out into some more rectangles? Let's see here. So we could maybe approximate this first little bit with a rectangle. I don't know, can people see that rectangle I just dropped? Okay, let me see if I can use pink here. Anyone see that pink rectangle I just dropped? I'll assume that you can. And then maybe we approximate this section with a rectangle, and then this section with a rectangle. Okay. Now, so the total area then could be approximated as A equals you know, the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle, which would equal, right, it'd be like A1 times H1 plus A2 times H2 plus A3 times H3. Are there any questions with this approximation of the area underneath this curve? Okay. What, so we've got some problems, right? We've got some area that isn't being captured right now. Let's see. Right, we've got, oh, that changed the text. Interesting. Right, we've got some area here, and some area here, and some area here that we're missing in this summation. What kinds of things could we do to capture a better approximation of the area under the curve?
Could we use right triangles to approximate it?
You could use triangles. What about the size of the rectangles?
We could just make them much smaller, and that would give us a better approximation.
Yep, absolutely. So you can make smaller triangles or smaller rectangles and fit more rectangles in here, and you can use triangles. And so my proposal is that we do both of those things. So instead of using triangles, or using rectangles or triangles, what if we did trapezoids? Everyone see the lines I just drew here, the one, let me see if I can erase that, oops, maybe. So let me see if I can. Everyone see those pink lines, and I'm also going to go ahead and draw another rectangle here and actually connect up with another triangle. Can everyone see that how we're capturing more of the area under the curve? We're capturing the area under the curve more accurately with these trapezoids?
Yes.
Okay. Yeah, now we're only missing a couple of sections. So does anyone remember what the equation is for the area of a trapezoid? Oops. So I'll help you guys out here. The given equation is A plus B times H divided by 2. And where, and let me draw this here, where H is the, in our case, the width of the trapezoid. And then A is the height of one leg of the trapezoid, and B is the height of the other leg of the trapezoid. See if I can. And very conveniently, the height of the trapezoid is equal to the height, the A and the B value. Well, here, I'll skip that for a second. We'll come back to that. So we've got A and B and H here. Now, if it was a perfect rectangle, like if you could approximate it by a perfect rectangle, that would be if A and B are the same, right? If the trapezoid's two legs were identical. And so then you'd have A plus B, where B equals A. So you have A plus A, you'd have 2A times H over 2. And it would just reduce down to A times H, which is the area for a rectangle. So that's a nice sanity check that this works. The other sanity check that you can do is a trapezoid in this case is just a combination of a rectangle and a triangle. And so you can find the area of the rectangle portion of it and then add it to the area of the triangle portion of it. And you'll get this equation for the area of the whole trapezoid. Does this equation for the area of the trapezoid make sense? Okay. So sorry about that. So if we've got, if we're going to use these trapezoids, what's going to happen is we've got the area, to calculate the area, we're going to have, number one, because it's easier for a computer to do, we're going to make all of the trapezoids have the exact same width. So we're going to use the exact same H for every single trapezoid, okay? And so what we end up with is that times A1 plus B1 plus H times, you know, my Alexa speaking now, A2 plus B2 plus H times A3 plus B3. Does this combined area based off of the summation of all the areas of the little trapezoids on the inside make sense to everyone? Okay. Is someone asking a question? Yeah, Juliana?
So
Oh,
how,
sorry.
how do we decide
I forgot about the cube, sorry. Is that what you're gonna say?
wait.
There's a
Oh, I was
divide by 2 here. Sorry, keep going. I'll put this in when I ask your question.
Okay. How do we decide what we want the width to be? Because wouldn't it be a balance between accuracy and computational intensity? So how do we decide the balance?
Oh, good question. So yes, you're completely correct. Theoretically, it is a trade-off between computational efficiency and how accurate it's going to be. The way we've been handling it is we make our H equal to the distance between the data points that we get. Because again, in real life, our error function is not a smooth function that we're getting. It's a whole bunch of data points that we're getting from our sensor. And so our H is driven by the spacing that we have between the spacing between the data points. And I guess I should clarify that in our current implementation, the H is not actually constant then, because the clock on the robot could be slightly off. You know, we may not be running the loop at exactly the same time every loop. So there could be some variation in how much time we have between each individual data point. So we would actually be running with the H that is specific to the data points that we just got. Now we could make if we wanted to, we could make the H larger. We could have the H be, you know, every 2 data points or every 3 data points. There wouldn't really be a way for us to make the H any smaller though, just because we don't have more data points in between. Does that answer your question, Michael?
Yes, thank you.
Okay, awesome. So this technique is called the Trapezoid Rule, and it's a very common and very effective approximation for the integral. It works really well. People do it all the time, and that is how we get our area underneath the curve for this integral component of the total power calculation, is with the Trapezoid Rule. And again, we have a window that we calculate the Trapezoid Rule over so that we don't have the issues that we talked about in the last meeting about integral windup and sort of some of the instabilities that you can get when you calculate the integral over too large of a period of time. Are there any questions about how we calculate the integral? So congratulations, guys. You've now learned calculus. And, you know, it's interesting. Typically, calculus is split up into 3 to 4 years, 3 to 4, if you're in college, 3 to 4 semesters. And if you start taking in high school, usually those semesters are years. And there's a lot of really important stuff in there. But effectively, what you're doing for those years is calculating the slope of the line or calculating the area underneath the curve of a line. And a lot of what you learn in calculus is fancy ways to calculate these values, what we call analytically. So coming up with a mathematical formula for calculating the derivative or the integral of a function. And that's good and useful, and you need to know how to do that. What ends up happening, though, is when you get out into the engineering world, none of your data, or very rarely any of your data, come in as smooth curves. You're almost always working with real data and not functions. And so you end up resorting to curve fitting and simple derivatives and the trapezoid rule in order to calculate the derivatives and integrals of all of your data. And those are sort of the things that you learn in the first couple of months of your first calculus class. And those are sort of the techniques that you end up using 90% of the time, which I sort of find amusing. And also, you know, it's really nice to have computers because these techniques would be a pain without powerful computers. And so when people were doing this in the past, they really needed to have these sort of functional arguments, but now we have powerful computers, and it's just a lot easier to just sort of brute force it with these very simple techniques and let the computer do the hard work. Are there any questions on anything we've covered so far today? If there aren't, or after we answer any of them, what I'll do is I'll show you the PID algorithm that we're using right now on the robot in LabVIEW, and then that will probably be all the time that we have for today. So are there any questions or comments about calculus or how we calculate the derivative or the integral? Does it make more sense to your dad, Alex, or is he still looking confused?
He's got it now.
He's got it now? Okay. Well, if we've got Mr. Shanafo with us, we're good to go.
Okay. I have one question. So in the second case, would we really want the integral to be triggering? Because I had understood that the integral was supposed to fix the type of problems we see in the left side of the graph where it's just small error over a long period of time. So why wouldn't we just instead look to see if the integral changes a lot instead of trying to calculate the area under the curve?
Can you say the last sentence one more time?
So wouldn't we just want to see, like, if the integral remains within a certain bandwidth, and then we would trigger it instead of calculating the area under the curve?
So we're getting the integral from calculating the area under the curve. So we will need to be calculating the area under the curve to get that integral. Now, as far as looking at whether or not the integral is changing in order to know whether or not to trigger that, I mean, or know whether or not to include that term in the controller.
I misspoke.
Sorry,
I meant error changing, not integral.
Oh, error changing. So like to sort of see if it's steady.
Okay, so I understood we wanted the integral term to sort of contribute to the PID only when we experience rather small amounts of error for a large period of time, not when we have large error that quickly resolves.
Correct.
Okay, so instead of, wouldn't we just want to see, like, if the error remains constant rather than looking to see the area under the curve?
As sort of that, so basically look at the variation in the error in order to use that as the trigger for the integral.
Yeah.
I don't know. I'm gonna have to think about that one and get back to you. I've never seen anyone implement that as the triggering device. My immediate concern with it would be if we've got a fairly noisy set of stream of data coming in, you might see a lot of variation in the error, but it'd be sort of very high frequency as opposed to looking at something over a longer period of time. I think you would sort of end up with a similar effect if you did the option that we had yesterday, where it was only trigger the integral if the error is within a certain, oh, no, I guess it would still be different. I'd have to think about that, Joanna. That's an interesting idea. I've not seen anyone implement that strategy for triggering the integral before. I have to think about if there's any downsides to that. But we can try it. We can always write our own algorithm and see what it would do.
Okay, thank you.
Sure. Any other questions or comments? Okay, so let me see if I can clear this. Clear all drawings. Okay. So let us go to LabVIEW. Okay. So we are currently on version 3 of the PID algorithm. Actually, there might be a 3.1 showing around somewhere, but 3 is the latest I have on this computer right now. So this has been a bit of a work in progress. I started this in 2013, I think, fall of 2013. So I took a controls lab in which we had to do a PID algorithm and in LabVIEW, which was very convenient. And so I did it for the class and then modified it for use specifically for the types of applications we have in FRC. And so that's why it's sort of got the Mars, well, the now old Mars coloring scheme for the little block icons. And over the years, I've been adapting it to add additional features. And I'll talk about at the end, there's some features that I want to add or that we should add this summer that would make it a lot more useful. The reasons that we have our own are really come down to interpretability. So LabVIEW has PID functions built in, and they may be better now than they used to be. The problem with the LabVIEW PID algorithms, there's two. One, there's a lot of code. There's a lot going on there. It's a little bit hard to follow. And the second problem is that they tried to be helpful, and every coefficient, like the Ki, the Kd, and the Kp terms, they are all multiplied by Kp internally, which is a standard that exists in some older control algorithms that can be a real pain to tune. And for people starting out with PIDs, it's just really hard to tune it properly. And there also weren't very good options for displaying sort of the results and visualizing how the system was behaving. So that's why we haven't been using that. Other teams have picked up this algorithm. I know I saw a couple of years ago, I downloaded Team Titanium's code, and this was the year that they went to Einstein, and their I can't remember if it was their shooter or their turret or something, is using this exact, well, version 2 of this exact PID algorithm. It's sitting there in their code. They downloaded it off of Mars's repository and put it in there. So it actually has gotten around, probably more than any of the other code that we're currently using. So the way this works is we have the goal that we're trying to get to. Can everyone see my cursor, by the way? Are you guys able to see my cursor or no?
Yes.
Okay. So we have the goal that we're trying to get to. We have our process variable, which is typically our sensor value. So it is the reading of the current state of the system. And right here at the get-go, we are calculating the error. So we're doing that subtraction of the goal minus the thingy that moves curve, and we're getting the error. All of this stuff up here is dealing with how we reset different things. So when it first starts up, there's a reset that can happen. So I guess what I should say is, with the integral and with the derivative, and with the, for the derivative, we're fitting a curve over multiple points. And for the integral, we're calculating the area for multiple blocks of time. There's some memory embedded in that. And so if things change a lot, or if you're starting out for the first time, or if you suddenly change what goal you want to get to, or any of those things, the information that is stored in that memory may no longer be valid. It may no longer be useful to the calculation. It could even hurt the calculation for the PID. And so there's some extra work that's happening out here to handle different times that we should reset that memory. Are there any questions on what I just said there about resetting the memory? Okay. So all that resetting's happening here. And then what we've got is, because let's see here. So we've got two arrays that are in with the shift registers. And one of them is the error. So we've got a set of error points as a function of time, and they are recorded for a certain amount of time. Well, I should clarify, they're recorded for a certain number of data points. So you need to always have in memory a number of error points that is at least as large as the largest of the number of points that you're using for the integral, or the larger, or if it's larger, the number of points that you're using for the derivative. So you've got to have some amount of those points stored in order to be able to do the curve fitting, in order to be able to do the trapezoid rule. And then the other array that we have is the time array. So for each one of the error points, we have a corresponding time. And that's important because the loops don't run exactly equally every time. Sometimes the loop might take 20 milliseconds, another time the loop might take 30 milliseconds. And so you can't just, when you're doing like the curve fit, it has to be in real units. It has to be an error as a function of real time. And so we're also recording the time that these values are getting stored. So we have the error and the time for each one of these points stored in memory. And that's in these two array lines, the shift registers. Are there any questions about these two array lines, the error and the time arrays? Okay. Everything that's happening with what I just selected is focused on inserting new values of time and error and lopping and getting rid of the older values of time and error. Here we're using array subset functions instead of replaces or inserts, because we need to maintain the order in which the points are. So when we were doing the moving average, we could kind of just do the modulus and cycle through, because all we needed was the most recent set of 10 values, and we're going to just do the average. We didn't care what order they were in. Here we do care what order they're in, because we have to do the trapezoid rule and the curve fitting. So we have to be a little bit more careful with how we maintain our arrays of error and time. Any questions on inserting the values that we maintain the order of the data points? Okay. So we've got our ordered data points, and down here at the end, we've got our summation of, so we've got the command, which is the power that we're typically the power that we're sending to our mechanism. And it is a summation of the power components from the proportional component, the integral component, and the derivative component. And then we've got our proportional, integral, and derivative coefficients that we pick. And then what we've got here in the data lines are, for the proportional, we're multiplying the proportional coefficient by the error. So that's this line here. Okay. And then we're multiplying the derivative coefficient by the derivative, and we're calculating the derivative here. And so what we're doing is using LabView's polyfit function in order to fit the third order polynomial to our data points. And then here is where we are manually calculating the derivative of that third order polynomial, which is that second order polynomial. And the output of this is the derivative, or the estimation of the derivative at that point. The reason it's in the case structure is when we first start out, for the first couple of loop cycles, we may not have enough data points to perform the fit. And so until we have enough data points for us to perform the fit, we're not going to, we're just going to set our derivative term to 0. So we're not going to consider the derivative until we've got enough data points. Are there any questions on this block of code that's doing the derivative? Okay. And then if we look at our integral term, we've got our integral coefficient being multiplied by the integral approximation, which is being calculated here. And it is using the trapezoid rule. Basically, we've got the 0.5, which is the 1/2. We have h, which is this right here. So it's T2 minus T1, basically, is our h. And then our a and our b are our two most recent points. So that's a plus b here. So this is a plus b. Oops. This value is h, and this value is 1/2. And oh, Alex has gone out to Hal at 8 p.m. Okay. Has everyone left to Hal, or is most everyone other than Alex still here? Did anyone else leave? I guess, okay. Looks like everyone else is still here. I'm going to assume that they are. Are there any questions on how we're calculating the integral here with the trapezoid rule? Are there any questions at all with what I've shown so far with this PID algorithm? Okay. What I'll do here real quick is just show you all what the indicators and controls are on the front panel of this. And then I'll talk about some of the problems with this algorithm. So we've got our KP, KI, and KD terms. There is no integrated feed-forward controller for this algorithm. So we only have the PID coefficients. We have the number of points to calculate the derivative over. So that's the number of points that we're going to apply the curve fit to. 50 is probably way higher than we'd want for most of our applications. And then n-int is the number of points that we're going to calculate the integral over, calculate the trapezoid rule over. And again, 50 is, maybe you could do 50, but 50 is again pretty high for that. These are both inputs into the sub-VI. We do have the way to limit the input and the maximum powers that we can output in case, we've got, so for example, this here with the shooter, we never want to run the shooter backwards. So you'd put in a 0 for the minimum output. So you want to never let the PID algorithm output a 0. And then we've also got 2 different plots. One plot will be the process variable versus the goal. So that will be the thingy that's moving plot that we've been seeing. And then the other plot that we have is the relative contributions of the proportional term, the integral term, and the derivative term. So as you're trying to debug your system and understand why it's responding the way it is, like why it's going backwards or why it's being very fast or very slow, you can look to see whether the total power that you're sending is being driven by the proportional term or the integral term or the derivative term. So that makes it a lot easier to sort of see why you're getting the response that you're getting. Are there any questions about any of the controls or indicators? And again, I'd love to be able to show this on a real robot. It would make a lot more sense, I think, to sort of actually see the plots moving. But any questions so far? Okay. So the last thing I want to talk about is I'll just mention briefly some of the problems with or limitations of this algorithm. So one of the things that I'm interested in implementing, because it looks like it worked really well in Rev's algorithm from on the Sparks actually, is in addition to having this time window for calculating the integral, having a error band. So not turning on the integral unless we're within a certain error range. That seems like a really powerful option that Rev uses, and it seemed pretty effective. So having that as an option here would also be nice. Another thing is, if we're in a situation where we are, say, using the swerve modules and we only have the proportional term and we don't need the derivative term and the integral term, it would be nice if we didn't spend all the time doing the math for the derivative term and the integral term, since we're not going to use it anyways. And so it'd be nice if that math turned off, so we were giving the RoboRia a little bit less work to do. There are also some visualizations that we could do that might make things a little bit easier to tune. And it wouldn't be too hard to integrate a very basic feed-forward controller into this when it's just a constant value. And again, just give people a little bit more tools right off the bat with that. That's all I've got for today. Are there any questions or comments about what we covered today? Okay. What we'll cover next time, I'll go ahead.
Thank you.
No problem. What we'll cover next time is, I'll put out a poll for what time we want that to be. But the next topic will be sequencers. That will be a short topic. That will be 45 minutes, no more than an hour for sure. This topic took a little bit longer than I was expecting tonight. And then the next set of things will be all focused on autonomous. So I'll put out some polls for the sequencer timing, lecture timing, and the autonomous lecture timing. But that's all I got for you guys. So let me see if I can stop sharing the screen. Stop sharing. Okay. All right. Well, thank you guys. Let me know if you have any other questions. I don't think there's any code for me to upload tonight other than I'll put the PID algorithm up. That way you can download it from that same training repository.